ओके हम एस्टिमेशन प्रोसेस से गुजर आए हैं और मैं आज थोड़ा सा आप लोगों के साथ डिस्कस करूंगा गास-मार्कोव थ्योरम। और गास-मार्कोव थ्योरम आप लोग इसको ब्लू प्रॉपर्टीज़ के नाम से जानते हैं, यकीनन आप लोगों ने किया है, बट टुडे आई विल बी जस्ट गिविंग अ recap of all that, what blue properties are, what is Gauss-Markov theorem is. Properties of least square estimates. The Gauss-Markov theorem states that the estimates estimated from least square, they are linear, they are unbiased, they are best, and hence they are efficient estimators. OLS estimators we have done in the last slides, like when we have estimated the simple and linear regression model, and we have estimated the B0 cap, B1 cap and B2 cap. So B0, B1, B2 or any ratio that is being estimated by the ordinary least square, that is called OLS estimate. And OLS estimate is having the properties of linearity, unbiasedness and bestness. The linearity property says that is the linear function of random variables such as the dependent variable y in the regression model. It means that if the association of a parameter estimate, OLS estimate, with the dependent variable y would be consistent and constant. So that would create a linear effect. So that's why all the OLS estimates are linear in the nature. But in all those linear estimates, most of them are unbiased. Unbiased means that when we say that the true parameters become same as the estimated parameter, that is called unbiased parameter. And we hope so that in all the linear OLS estimates, most of it are unbiased. Their estimated value is said to be equal to the true value of parameter estimates. So this is called unbiasedness. And the bestness or efficient estimator, for which the bestness is important, it means that minimum variance property. It means that the OLS estimates, either it is B0, B1, B2, whatever, all the OLS estimates have minimum variance around around the residual mean. It means that if the estimates is having a least variance, then the estimate is more reliable, and it has a worth to be used in forecasting. It has a worth to be used in hypothesis testing. It has the worth to be used in interpretation and creating or extracting true meaning of any economic behavior. But if any parameter estimates, if it is not having a least or minimum variance, it means that the mean value of the parameter estimates would have been losing the reliability. So here we will prove that the parameter estimates of the from the ordinary least square process are blue. They are best, they are linear, they are unbiased, and they are efficient. We have done simple linear regression model, we have done multiple linear regression model, we have calculated so many parameter estimates, but I will be taking a simple linear regression model as a case where our model was y is equal to b0 plus b1 x plus u, and you know that we have estimated that model from the process of ordinary least square. We have drawn the estimators, we have done it from matrices and equation method as well. So in the case of simple linear regression model, we had this kind of model, y is equal to b0 plus b1 x plus u, and from these realizations we have structured the true regression line, we have structured the estimated relationship, and finally we have structured the estimated regression line as y cap is equal to b0 cap plus b1 cap x. And by using these realization, we have extracted the solution through OLS estimator, and that OLS estimator have given us two normal equation, and we have used these equation in solving the multiple simple linear regression model. That was first equation was normal equation for B naught cap, second equation for normal equation for B naught 1, and from this normal equations we have extracted these formulas. So these were the ordinary least square estimates. Estimates are B naught and B1, and these are the estimators. So so far as the Gauss-Markov theorem states that these two estimates are linear in nature, they are unbiased, they are best in its own self, and from these formulas we have established the deviation formulas as well, and we have already proven that these formulas and these original form of formulas are same, and we have extracted from these similar normal equations. So moving on, we have to prove the linearity and biasness and bestness of the parameter estimates B naught and B1 for the simple linear regression model. So we will start from the first estimates B1 cap, and B1 cap I've shown you that we have deviated formula like small sum of small x into small y divided by sum of small x square, and we know that small x and small y means the deviation of x and y. Small y can be obviously converted to its deviation form. Obviously the x, small x, is also is the form of the capital X minus capital X bar, but here we are just replacing small y with the with its value, and by multiplying summation x from the from this bracket we have this composition, and we know that summation small x is 0 because deviation, the sum of deviation of any variable is 0. You have also done that. So if I put this 0 over here, so I'll be getting so this is I've just shown you the proof of it, but anyway here I am just putting it 0, just then we get only summation x into y divided by summation x square, and I have just written into this form. I've just taken common that summation y from this equation, this expression. Now I'm just replacing this x over summation x square as k. I'm just putting a name to it, that is k, and the linearity has been proven here, because how it is linearity is proven here, because we know according to assumption number according to assumption number it is all I think it is equation number first, or it was a second equation in the usual OLS assumptions, that x is having a fixed factor in repeated sample case. It means that x is a fixed factor. It means that x is having here as a constant term. It is not a constant, pure constant, it is a fixed variable, so that's why the x or summation of x square become a fixed ratio or constant. So that constant has been replaced by the ratio k. So this k is being is introduced as a ratio factor through which B1 cap is concluded as associated to y, and we know that the variable, any variable, if it is associated with this with its determined factor with the constant ratio, that is said to be linear, that is said to be having linear association. Here linearity is proved, where we can say that the B1 cap is associated or related to y with constant ratio k. So there the linearity is proved. So now I'll be doing some more explanation here. I'm just taking some that b1 cap equal to summation ky I've taken from this expression, the last expression. I'm just following this statement, and I'm just taken the expression some b1 cap is equal to summation small ky. I'm just putting the value of y, because we know that the capital Y is simply our model, that is b0 plus b1 x plus u, and by multiplying k we get this expression, and in this expression summation k and summation kx has been replaced by 0 and 1 respectively. We have replaced summation k as 0 and we have replaced summation kx as 1, and why we have put it as 0 and 1, this is being proven in this box. You can see this summation k and summation kx, how it has become 0 and 1. Okay, you can see in the box, and when I multiply b0 with the 0, that becomes 0, and b1 is multiplied by 1, that becomes b1, and summation ku is left. So by taking expectation we get the expression like that. Estimated or expected value of b1, that is equal to expected value of b1, true b1, and we know that expected value of true variable is always true. So that b1 becomes remained here, where that expected value of this expression would be applied to u only, because k is of constant factor, and and expectation doesn't apply on the already summed factor. So that's why summation expectation would be applied on the variable, that is u, and sum of u or variable of u that has having expected value, that is according to assumption number residual assumption number 1 is 0, because we know that the mean of u is 0. So that's why you can see that the estimated value of b1 cap become a true value of b1, that is linearity. And here how this summation kx I have put equal to 1 in this box, that has been proven. You can see, and you can do it by yourself. Now I have explained the linearity and unbiasedness. Now I'll be proving the bestness of the b1 cap. I'm taking again that expression here, and after that I've just taken the variance, and by taking variance, that b1 cap becomes variance of b1 cap, and here the variance of this term. Remember one point, that any constant, like here we can say that that is k, that k is not a pure constant, that is associated to one variable, that is being obviously defined k in its x in itself. So that's that constant ratio is not a pure constant, and here it is associated with y. So whenever any constant associated with variable and we take the variance, then that constant become of its square. So sum of a square becomes like sum of k square, that become the result of taking variance, and variance would be applied on the variable only. If there were only k as a pure constant, the variance of k would be 0, because constant is having variance as 0. But here the constant k is not a pure constant, this is associated with the variable y, then the variance would be applied on the y, and the coefficient associated with this variable would become a square. So if I take the square, so we know that the k value is taken as this. So I have just put the k value over there, and just simplifying this this expression, where we have taken variance of y as variance of u. Why this is variance of y is equal to variance of u, that will be obviously proven later. Obviously in number 4 box. that is actually the reason why I've taken the variance of y as sigma square of u, because the variance of y mean by virtue of definition the variance is the mean of the sum of the square of the deviation. So that is the mean of the sum of the square of the deviation. A mean of the square of the deviation is called variance. So here we have taken the deviation y minus mean of y, and we have taken the square of it, and then we have taken the mean of all this square deviation. So that is actually the variance of y, and by putting y and e of y from the realizations earlier, we have shown that that is y is equal to b naught plus b1 x plus u, and e of y as b naught plus b1 x. If you remember, I've shown you all the realization in previous slide. From here I have taken y, that is b naught y, that b naught plus b1 x plus u, and e of y as b naught plus b1 x. That has been explained very earlier in our lectures. So thus how I have changed this variance of y as the variance of u. So here we have changed this variance of u, and here we have opened the square, sum of x square and sum of x square above square. So one factor is divided by the two factors, that is being cancelled, and ultimately we have got the variance of b1 cap as like that. That is the variance of b1 cap, which is estimated by ordinary least square, and assumption says that assumption says that if ordinary least square having the minimum variance, it means that the variance of b1 cap you are seeing here, that is having a having a minimum magnitude. If this b1 is estimated by any other method other than OLS, that variance would have been more than this. It means that if I estimate this b1 from any other method other than OLS, so the variance of that b1 would be larger than this. Let's say if we take that b1 is estimated by OLS, and we have given the notion of cap above it, so that b1 cap said to be the variance estimated by ordinary least square. Let's estimate this variance, let's estimate this parameter estimate by any other method, whatever the method it is not OLS. So that would be something like that. That would be summation cy instead of summation ky, because you know that the k factor was extracted from the ordinary least square process. If you remember, look at here, that k was replaced by this factor, and this factor was extracted from this formula. It means that the k factor is being driven by ordinary least square process. If we change this k, it means that I am not following the OLS process, I am following any other method. So keeping this analogy, I've just changed that k with c, where b1 double bar is the parameter estimated by any other method than OLS, and c is a ratio just as k, but with a little measurement difference as d. Obviously, if we assume that by changing that k to c, if estimate will show any kind of difference, that would have been d. If by changing the method from ordinary least square to any other method, if d is 0, it means that there is no difference between the two methods. So for accepting that c in replacement of k by having assumption that there must be some difference, so that difference is added to this ordinary least square k factor, that would become c. So that's why we have taken c. We have assumed that that the C would be some kind of a factor, some kind of just as K that has been that has played the role in that expression. Here the C is making, or C is playing the same role, but with a little difference added to this OLS factor. So now I am taking variance again. Now keeping this expression, we are going to take another variance. Now it is the variance of not a variance of B1 double bar and not the B1 cap, because the B1 cap was estimator of the ordinary least square, but this is any other method we are following, so that's why we have changed the notion from B1 cap to B1 double bar. So now taking the variance in the same pattern, you see that when the variance is applied on y, that is being changed into summation square of u, and we have already proved in the previous slide. And now I am taking again that C factor, variance of that C factor, which is not a concrete or a perfect constant, but it is the fixed variable which is associated with the variables. So that's why if the variable which is associated with the constant ratio, so the variance of that would be the square of it. So therefore we have taken the variance of it, and we know that the C is actually the key plus D. So now we are opening the parenthesis, the formula of A plus B whole square, so we get this one, and by applying a summation sign and as well as the summation sigma square of u, I've just multiplied this summation sigma square of u with the summation sign on only K. I've just separately I have applied this summation square of u and summation with K, and sigma square of u with summation sign is applied by the rest of the factors separately. So that summation square of u into sigma square of u into summation of K square is being explained like just as I did before in the last slide by explaining the variance of B1 cap. That summation K square is actually the it is equal to the 1 over summation small x square. So then by proceeding further, so we know that this expression is equal to variance of B1 cap. Variance of B1 cap, and B1 cap is the factor which is estimated by the ordinary least square. So here you can see that the variance of B1 double bar is the summation of variance of B1 cap plus some factors. Obviously when it is the summation, so it is being proved that variance of B1 cap is less than the variance of B1 double bar. So it is proved that the ordinary least square estimate is having a minimum variance if the estimates are being estimated by any other method than the OLS. Now in similar pattern we will be proving the blue for the B naught. And B naught cap, as I said, as we have established that B1 cap is equal to y bar minus B1 cap x bar. So by opening the y bar, I get this expression as we know that the y bar is the mean, which is the having estimator of summation y over n, where the B1 cap is summation ky. I have taken from the linearity of the B1 cap. So by taking a common of summation y from this expression, I get this, and we know that in the parenthesis all the terms are constant. N is the number of observation is constant, x bar is the mean of x, it is constant, and k ratio is already being established as a fixed ratio. So that's why this all parentheses, all this internal factors of this bracket that has been considered as constant, we just name it as D. And here again we can see that the B naught cap is associated with the y with the constant ratio D. D is not a pure constant, but it is a fixed ratio which is associated with the variable y, and that expression actually proved, it is provide an evidence that the linearity of the B naught over y, because the B naught cap is associated with the y with a constant ratio D, so that comes from the linearity of the B naught. And if we continue with this to prove other properties, I'm just doing the unbiasedness. Now I have taken the b naught cap is equal to summation into 1 over n minus x bar k into y, the expression from the last slide. And just I am just taking the expectation of this expression, and you see that I have taken the expected value of the b naught cap here, and on the right side I have just taken the expected value of y only, because summation already summed expression doesn't have another mean or having expected value according to the rules. So expectation is applied on the variable, and we know very well what is the e of y means. E of y means b naught plus b1 x, and by multiplying these two brackets I am getting this one, and by applying the summation sign I am getting this one. If you see that the summation sign is applied on the constant that is turned into the n, and then summation sign is applied on the k, because x bar is pure constant, b naught is pure constant, but k is not the pure constant, it is associated with the variable taken from the OLS estimator. And here I have taken the sum of x, because b1 and n is constant, and here b1 is constant, x bar is constant. I am taking the sum of summation of kx. And we already know that summation k is equal to 0 and summation kx is equal to 1. We have proved yet in the last slides. So I am putting these values over here, and by getting 0, that term would be obviously fizzled out, and by applying multiplying this by 1, I'll be getting this. So you can see that one is positive factor, one is negative factor, they both cancelled out each other, and here you can see that expected value of b naught is equal to true value of b naught, which is the sign of unbiasedness. Now the bestness property, we know that what bestness property is. It is the OLS estimate is having least variance. We will prove it by the same manner that we will be estimating the variance from OLS estimate. We have established the OLS estimate as b naught cap, and after that we will be establishing the b naught from any other method. We would be noting that one by the double bar. So first of all I am taking the b naught cap. Cap is obviously specifically applied to the estimates driven by the ordinary least square, and if I take the variance of it, so you know all the schemes what have been happening from the expressions. Variance of b1 cap has been taken here, and variance of y has been taken here, and the constant associated with the variable that has been squared in the expression. So variance of y has been changed to summation square of u, and summation the rest of things are the same. And by opening this the parenthesis, by putting formula of a minus b whole square, so that expression does like it. And now I am again applying summation. Summation is applied on the constant by the term of n. Summation is applied on the k. Summation is applied on the k square, because rest of the factors are constant, and constant is already always comes first as a coefficient to the variable. So then by simplifying this, summation k, as I know that it is equal to 0, and summation k square I have already proven that it is equal to 1 over summation small x square. So by doing this I am getting this expression, variance of b naught cap is equal to sigma square of u into 1 over n plus x capital X square divided by summation small x square. And capital X square is termed as like that because we have already proven in the last slides, because how it is like that. If we explain this summation small x square, and if we open it, so we will be getting summation x x bar square. Sorry, it is yes, it is x bar square, summation x bar square. So here the variance of b naught cap has been derived. If you find any kind of a confusion, if you have any question, you can ask me on my WhatsApp, or you can mail me, or you can WhatsApp me. I'll be giving you the answer of it. And now I'm just taking the B naught double bar as the estimator driven by or estimated by any other method than ordinary least square, and here I have just changed the factor of k with the c, and you know what we mean by c. C is the factor as same as the k, but added with this some difference of the different method, so that's why c would be k plus d. So here I am taking again the variance of it, and you know the variance of B1 B naught double bar is taken, and here the variance of y has been taken, and this parenthesis is taken as a constant associated with the variable, and that's why it is being squared, and variance of y becomes sigma square of u, and the rest of it factors are the same, and by opening this squared parenthesis I will be getting this, and by applying summation sign again, same patterns and same expressions are repeating again, and we get this because we presume that similarly that as summation k was equal to 0, there is summation c taken as 0, and summation is applied again over here, and the c is being now changed to k plus d, as we know that the k plus the addition with the addition of some difference becomes c, and by simplifying this we get this expression. If you have any query, because this is 0, that has been fizzled out, rest is the same, and now the thing and the thing to be noticed carefully and keenly is this, that now I will be playing with this expression smartly. How? Look at this. I have just opened the k plus d whole square formula, then I have taken sigma square of u and x bar, because sigma square of u is multiplied by the whole factors, whole bracket, and x bar square is multiplied by with this parenthesis. So that's why sigma square of u into x bar square, that is being multiplied with the k plus d square minus 2dk. Here again you can see that, and I have just taken out the factor k only. Sorry, if I have taken out the factor k only, there should not be a k should be repeated. Let me clear it. Here I have corrected that because k has been taken as separate factor, so that's why it should not be repeated over here. So here the left factors are d square minus 2dk, and k has been separated here with the x bar square because it is being multiplied, plus 1 over n, that is from here, and sigma square of u, that is from here, and that sigma square of u with summation x bar square, that has been multiplied by the rest of the factor. Now that factor would remain same, and you can see that I'll be explaining this factor. So this factor, we know that summation k square is as same as 1 over summation x square, and by simplifying that I'll be getting this, and you know that all this is happening again just as a previous slide where I've proven the variance of B naught cap. It is just repeated over here, and this is actually the variance of B naught cap, because these 3 or 4 steps I have already done in the last slide. So here you can see again that variance of B1 double bar is equal to the summation of variance of B1 cap plus these factors. So obviously when the variance of B1 double bar is the summation of some factors, so that's why it is obvious that this variance of B1 bar would be larger than the each of these factors. So that's why it is being proved that the variance of B naught cap is less than the variance of B1 double bar. So my dear fellows, we have done we have seen the Gauss-Markov theorem, where the Gauss-Markov have said that the ordinary least square estimate would be having a linearity, definitely, obviously, and then out of those linear parameter estimates, most of it would be unbiased. We have proven that the B0 and B1 are linear and B0 and B1 are unbiased, and the third property was the best property, which stated that the variance taken by the ordinary least square estimates would be less than the variance of those estimates which is being estimated by any other method than OLS. So we have proven all these properties. These properties are being called blue properties as well: B for bestness, and L for linearity, U for unbiasedness, and sometimes E is being mentioned as efficient factor, because a parameter estimate which possess all these three properties are considered as efficient factor. So guys, if you have some kind of a question, problem, because I've been doing this in little bit speedy, if you want to know something, or if you want to get explanation in little bit slow speed, you can pause it, you can slow it down the video, you can hear it clearly. And if again, if you find some kind of question or query to ask me, you can WhatsApp me, you can email me, you can ask from the by putting comments on following the video. Thank you very much. Thank you.